Hi guys, so here I am again. So something happened, so I got copyrighted. So I do have to record this again. I mean, which is kind of nice, so because I kind of went over this with you guys, so then this will be a lot more easier the second run than the first run. Um but yeah, so I got copyrighted, so I have to record this again, but it's not a problem. It's better sooner than later, right? So I really appreciate the people that just let me know that the audio wasn't on for this video. So if you see that it was re-uploaded, then yeah, I did upload it again. So I'm sorry for any problems with the audio or anything. But I guess we can get started if you guys want. So then 7.8, unimolecular reactions. So we have SN1 and E1. So the rate of SN1 and E1 reactions are first order. In other words, they are just dependent on the concentration of the substrate, meaning that our rate in this case is gonna be rate equals K times substrate. Meaning if they ask you in a test, for example, what will be the rate for this one, and it's SN1 and E1, they will only care about the concentration of your alkyl halide. They wouldn't care about the rate of your base or your nucleophile. They only care about the concentration of this. So then if they told you, oh, if we double the concentration of your alkyl and then we double the concentration of your nucleophile, then technically the rate will only double 2 times, since we only care about the concentration of your substrate. So both mechanisms deal with a loss of leaving group, giving first a carbocation intermediate. So what's interesting about unimolecular reactions is that they have their first order, they're unimolecular, meaning that everything happens stepwise. So when I mean uni one, so one step at a time. So then unimolecular are mainly like multi-step. So unimolecular, either SN1 or E1, they're always gonna start with a loss of a leaving group. So then, when we have a loss of a leaving group, we always get a carbocation intermediate. So then we have a loss of a leaving group in here, and then we have a carbocation intermediate. So that will be our first step, either if it's SN1 or E1. And then after that, when we get our carbocation intermediate, it depends whether we have a base or a nucleophile. So we already know substitution, it's always gonna be a nucleophile, while for elimination it's always gonna be a base. So just keep in mind that when we're doing SN1 and E1, the first thing that we do is a loss of a nucleophile, and then our second step, it will either be substitution or elimination. So we can get started with SN1 mechanism. So for SN1 mechanism, there's an extra step technically, but it's kind of like a hidden step. It's still like a two-step, but the thing is that we add an extra step just to make it more stable. It's kind of like an add-on per se. So then we have an extra step or an add-on. So like we said, we first proceed with a loss of a leaving group, and then, since we're doing a substitution reaction technically, we're gonna do a nucleophilic attack. That will be our second step. So then you see here that our oxygen has a positive. So in this case, we want it to be like the most stable it can be. So for it to be the most stable, we want an oxygen with 2 bonds and 2 lone pairs. So for that, we're gonna get our For that, we're gonna draw our, technically we're gonna put again our nucleophile. Like, it's gonna show up another time. Our nucleophile is gonna show up a second time, and it's gonna take that extra hydrogen that our oxygen has and making our oxygen more stable. So then it's technically like our oxygen has 3 bonds now, and we have a possibility of making it more stable. Therefore, our nucleophile is gonna technically take that extra hydrogen that oxygen has, and it's gonna give us a more stable product. So just think about it. If you have like a positive charge oxygen or anything positive charge as one of your products, then you can always make it more stable by just removing that extra hydrogen. So that's the third step. It's an add-on. It's technically like an add-on. So it's not really mentioned, but if you want to make it more stable, then that's going to be your product. So SN1 reactions. SN1 reactions are unimolecular. Remember, unimolecular, one step at a time. Since it involves only one chemical entity, the substrate, therefore SN1 is believed to be unimolecular nucleophilic substitution reaction. And again, we go through it. We first have a loss of a leaving group, giving rise to a carbocation intermediate. Then our second step will be a nucleophilic attack. And if we end up having, a positive charge with a hydrogen, then we add on a third step in which we do like a proton transfer kind of thing, just to remove, that extra hydrogen. So then we can move on with E1 mechanism. So E1, it can happen on tertiary. I did put it on tertiary because on tertiary it's more faster, but that doesn't mean it can happen on secondary or primary. It can happen, but rarely. So we mainly see it on tertiary. So tertiary alkyl halide undergoes ionization. This is a 2-step elimination process in which the first step is a loss of a leaving group. Oops. So then, like I said, no matter if it's an SN1 or E1, it's always going to start with a loss of a leaving group. That's when it's unimolecular. So when it has that one means unimolecular. So then what makes it different is that in this time, instead of a nucleophilic attack, we have a proton transfer, giving us kind of like a hint that we're going to do an elimination reaction. So E1 has the same rate of reaction as SN1. It's K times the substrate. Our rate is going to equal K times substrate. And E1 is an unimolecular and is referred as unimolecular elimination reaction. So what's the mechanism? So like we said previously, since I have to record it again, I do have some notes I forgot to erase. So E1, like we said, we always start with a loss of a leaving group, and we have our determining step, which is a proton transfer. And you already know from E2 how proton transfer works. Our base is the one that takes away that hydrogen from it. And then, when it takes technically like that hydrogen, we have a positive in here, and then we have a negative in here, and then we just make a double bond with that one, giving rise to what we have. Oops, I don't know why I drew it like that. Giving rise to what we have right here. So it's technically like they just put it in this way just so they don't have to do, this multi-step process of drawing two things. They just said, oh, this broken bond, it becomes a double bond in here. But I like to do it multi-step just because it's way easier for me to see, oh, what's going on. So overall, E1 mechanism, we start with a loss of a living group and then we do a proton transfer. So again, SN1, E1, notice that we always begin with a loss of a living group and giving rise to a carbocation intermediate. You possibly know that by memory right now. So then again, okay, SN1, substitution reactions has to do with nucleophiles. Elimination reactions have to do with base. And since we're doing unimolecular reactions, unimolecular, our first step is gonna be a loss of a living group. And then our second step is either gonna be a nucleophilic attack or a proton transfer. So let's practice. So draw the carbocation intermediate that is expected when each of the following alkyl halides undergoes ionization. In each case, if the carbocation is resonance stabilized, make sure to draw the resonance structures. So then what I mean in other words is that we're gonna try to get our carbocation intermediate. Just a little hint, remember that we have our stability goes from primary to secondary to tertiary and to this for carbocation. So then we have resonance stabilized. And the stability goes like that. So then if we have some resonance, then we will show it. I will show you how to do that. So then try it on your own. You can do it on your own. So then I personally always like to draw my lumpers. So then we can begin. So in this case, to get a carbocation intermediate, we're gonna have a loss of a living group. So then we're gonna break this bond and then we're gonna put it on that chlorine so we can get a carbocation. And the thing why I like to draw lumpers is that you can visually see where those electrons from that broken bond went. You can see that originally we had 3 lumpers and now we have 4 lumpers on that chlorine, meaning that extra lumper, it came from that broken bond. And since those lumpers, they didn't go to our cyclohexane, that's why it has a positive charge, because the lumpers, they didn't go to that carbon, therefore it has missing electrons. That's why we can make an extra bond in there. Okay, so then these ones will technically be our products, technically. Just for now, until we can do like a substitution or a nucleophilic attack, depending on the base and the nucleophile. So next, if we try to do the same logic in there, we're gonna break that bond. But I think since you're aware that we have a double bond right there, I think you can see that we're gonna have some resonance right there. Oh no, that's not that pretty. So then if you remember your resonance patterns, I can always move a double bond next to a positive charge. So then my positive charge goes where my double bond used to be. So that will be like my resonance structure. So I'm showing resonance because we said that resonance more stable than a tertiary. Okay, so now you can try it on your own. Okay, perfect. So then we're gonna draw our lumpers right here, and then we're gonna break our bond. This one's pretty straightforward. And it's just gonna have a positive charge, and then we're gonna have our bromine down there. And it's the same logic that we used before, that those electrons from that broken bond, they went to that bromine, giving us another electron pair on that bromine or lone pair. And then we have a tertiary carbocation. And then for the next one, sadly, you're gonna have a lot of resonance structures. So then when we break this bond, we're again putting those electron pairs on the iodine, and we put it on the halide because it's a halide. It's, you know, like things like fluorine, chlorine, bromine, iodine, and they know to be electron drawing, so they draw electrons towards them. That's why the electrons go towards them instead of going towards that carbon. Okay, so we have a positive charge in there, and then we have our iodine. And technically our iodine is not involved anymore. So then we're just gonna draw some resonance structures. Okay, so I just moved it so we can actually draw a little bit. So then again, I'm gonna put our iodine negative in there. Okay. So then we can move that double bond next to that positive charge. And then we're gonna place that positive charge on where that double bond used to be. And we're gonna repeat that same pattern over and over. So then double bond next to that positive charge. Okay, perfect. Let's see. And I'm gonna move this one next to here. This, and then I have positive charge in here. Okay, and then my next resonance is gonna be this one, this one. Then I'm gonna do that again. I'm gonna place one of my double bonds next to my positive charge. Give me rise to this product right here. And this one will be all my resonance structures. And so I will have a total of 5 resonance structures for this figure. So yeah, I also put out this problem because I wanted you guys to practice a little bit on resonance, just because it's gonna appear on the final probably. Not as hard as this one, but I still want you to be able to move out your electrons. Okay, so carbocation. We have carbocations in this case with E2 and SN1. So we are gonna have rearrangements. So the first product can be done through, so I'm just gonna put out a couple of examples. So the first product, it can be done through SN2 processes, but the second product has rearrangement, which can only be achieved with an SN1 and E1 process. Okay, So then if you look at this one, down here, we can totally do that by a substitution reaction without any rearrangements. But then you can see that the second product, it looks a little bit odd, right? It doesn't look like so then when we break our bond with our bromine, it's gonna look like this, right? So you're gonna be like, well, that second product doesn't technically look like that, right? It doesn't look like that water, it went in there and then technically just attacked it and then just replaced the place where bromine was, did it? It doesn't really seem like it. It seems more like the first product, right? The thing is that the first product, like it said, it doesn't have any rearrangements. While the second product, it does have rearrangements. And from what we learned from carbocation rearrangements, it's mainly about stability. So again, we have the same rules. So then a resonance stabilizer more stable than a tertiary, then a secondary, then a primary, and it just goes on like that. So then remember that with rearrangements, we're able to either do a hydride shift, meaning we're moving just a hydrogen, or we're able to do a metal shift, meaning that we're moving a CH3 group. I'm sorry guys. So then we're gonna get started, and then we're just gonna remove that highlight from there. And then we have a bromine negative. Okay, so then in here we have a secondary carbocation. And then technically the logic that we use is that we have that carbon in here, so then we have to look at the carbons next to it. We only have 2, and we have to see what they're attached with. So then this one has 3 hydrogens, so if I were to do a hydride shift, meaning let's see, meaning if I was going to move one of the hydrogens in there, and then, just erasing it. And just putting that one as a positive. If we count carbon-carbon bonds, technically I would only have a primary, but primary is not more stable than secondary, therefore I wouldn't really recommend to do that. So I don't think we can look at the carbon up, so then we can look at the carbon next to it. That one has only 1 hydrogen, so we can either do a hydride shift or a metal shift. So I would recommend to do a hydride shift, just because if we move that hydrogen, meaning we put it in here and then we erased it, and then we put that positive charge in here. If we count our carbon-carbon bonds, we have 1, 2, 3, we'll have a tertiary carbocation, meaning that that one will be more stable. We didn't do a metal shift, just because, you know, if we move our metal and then we put it in here and then we raised it, if we count our carbon-carbon bonds, we have 1 and 2. It will be secondary. It will be a secondary carbocation, so it wouldn't really make sense to do that shift going from secondary to secondary. That's why I really advise you to instead just do a hydrate shift. And if we do that hydrate shift, we have our tertiary carbocation. And then, you know, we're just gonna proceed that water is gonna attack that positive charge. And then, you know, we have our add-on step. That add-on step was the one that removed, you know, that a hydrogen from that positive product that we got. Which is just making it more stable. So it's just an add-on. It's kind of like a hidden third step. So that's the reason how we're able to get the second product as well. And this is just a summary on how we were able to get that product. How did we achieve the second substitution product? We first did a loss of a leaving group, then we did a hydrate shift, a nucleophilic attack, and then a proton transfer. So like we said, we always proceed with a loss of a leaving group. We made it more stable from secondary to tertiary. We decided to do a hydrate shift. Then, you know, we're doing a substitution reaction, therefore we're going to do a nucleophilic attack. And since we have an extra hydrogen in there, we just bring back our nucleophile to take out that extra hydrogen that we had, meaning we do like a proton transfer, and then we got our final product. So as we said, with carbocation rearrangements, there's not only hydrate shifts, we also have metal shifts. So then in this other example, let's see, you can see that the first product we can again just get it without rearrangement, but the second product is with rearrangements. So then, like we see here, we have first a leaving group, then a second we have a metal shift. So then in here, when the bromine leaves, we have something like this, right? We have a secondary. And just like the same logic as the previous one, in here we have a carbon, hydrogen, hydrogen, hydrogen. If we do a hydrate shift, we will get a primary, therefore it wouldn't work out for this one. So then luckily we can look at the one next to it down on the left, and we don't have any hydrogen, so the only possibility is doing a hydrate shift. But luckily this one has 4 carbon-carbon bonds connected to it, like we have 1, 2, 3, and 4. So meaning if we do like a metal shift, it will give rise to a tertiary carbocation. Let's see if we erase that one, and we put that, you know, that CH3 in here, and we put that positive charge in there. If you count carbon-carbon bonds, you can 1, 2, 3. We'll have a tertiary carbocation, meaning it's more stable than a secondary. Therefore, we're able to do that shift. So we're gonna do a metal shift. And then we're gonna have a nucleophilic attack. We have an extra hydrogen in there. We have an oxygen positive, so there's a possibility of using our nucleophile to take out that extra hydrogen that we have so we can get our final product. So trick questions. There's a trick though if we look at this sample. The first alcohol cannot be formed due to steric factors, and it cannot be formed via SN1 pathway. But product 2 can be formed by doing a carbocation rearrangement via SN1 process. So then, let's see. Okay, so then in here, if our group leaves, meaning if that bromine leaves, we'll get something like this. And technically we'll have like 2 hydrogens hanging from it. So we'll have like a primary carbocation. So then technically it wouldn't be like the most stable. It wouldn't be the most stable thing possible. So then we will prefer to do a rearrangement. And you'll be like, well, why we're not able to, to use to afterwards use to a nucleophilic attack. The thing is that now we're gonna start thinking like we can do E1, E2, SN1, or SN2. So the thing is that with SN2s, with SN2s or E2s, we normally have like negative charges placed into them. With SN2s, when they're normally like very small, like something like OH or OCH3 negatives. SH per se, because sulfurs they're very reactive sulfurs. While with things with E2, we can also work out with oxygen with OH negative, OCH3 negative. But the thing is that E2s can also be very bulky, unlike SN2s, which they have to be really small. So we can have things like turbute be okay. And with E1 and SN1, they are normally in a combination. So if you have E1, there's a probability of having SN1. It just depends on the situation. And E1 and SN1, they're normally like, they have, they're stable. They don't have like a negative charge. They don't have any positive charges. So we can have things like this. So you can see this one doesn't have any, this one doesn't have like any negative charges. So that kind of technically eliminates SN2 and E2. We can technically think about doing SN1s. I would say maybe some elimination products. Let's see if we have in here positive. Then So from here, technically not, but after we do a, like, from this one, technically not. So we have to do a rearrangement first. So, you know, we will technically do a metal shift. Let's see, 1, 2. I want it to look the most like it possible. So then let's see. Okay, so then once we do that, our positive goes there. We have 1, 2, and 3. So then we have a tertiary, meaning that that one's more stable. So if you think about it, it technically looks like this. And now, if you look at it, we're technically able to do also elimination reactions. Just because we need, for us to be able to do an elimination reaction, we need to have, we have our alpha, and then we have our beta. And then our betas do have hydrogen, so then we are technically gonna be able to do, we're technically gonna be able to do elimination reactions as well. But now we're just looking at SN1 reactions. So then those are kind of like the reasons on why this one is not observed. Just because we already explained that E2 and SN2, they normally happen on negative charge things, while E1 and SN1, it happens on things that they're a little bit more stable. Also because it's saying that it happens in heat. SN2s don't happen in heat, they happen at room temperature. And also because of steric factors, when it's like, when it's bulky like that, then technically, when it's like really bulky like that, then technically SN2s cannot happen. So then this is just like a step-by-step on how we were able to get this substitution product. So then, like we said, we lost that bromine. We have we're giving rise to a primary carbocation, but then we did a metal shift, so we have a tertiary carbocation now. And you can see here we have our bromine group. Then we were able to do that substitution. So then we were able to do a nucleophilic attack. And then, you know, you can see that our oxygen has a positive charge. So then why not make it more stable? So then we just bring back our nucleophile again, and for it to take that extra hydrogen that we have, so we can have our final product. So then substrate effects on ionization rate. So then we have fluorine, chlorine, bromine, and iodine. So if you think about it, in a periodic table, it goes like this. For just when we're doing reactions, but then afterwards it's gonna go like that. So then the more reactive, the faster the reaction is gonna be. So then when can SN1 and E1 happen? SN1 and E1 are observed for tertiary alkyl halides. So then you're gonna see them mostly on tertiary alkyl halides, but they are rarely observed on secondary or primary halides. Rarely doesn't mean that it doesn't happen. It can happen, but you barely see it. There are a few exceptions though, such as resonance stabilized carbocations. So then, let's see. Carbocation and resonance stabilized position, therefore it's possible to do SN1 or E1. So then, for example, if our group lives in here, we have a positive, and then we have a resonance stabilized. So then, technically, we cannot do like any more like metal shifts because that's like the most stable that we're gonna get. So then, we don't really have to worry about any metal or hydride shifts. And then let's see. So from what we learned before, we're gonna start looking at our bases or nucleophiles. So then if we look at this one, that one seems pretty stable, right? And then we said that things that are kind of stable, they don't have a negative charge and that they act in heat, they're normally gonna be E1 or SN1. That's why we're given these products. So then, like I said, technically we have a resonance stabilized. In this case, when our bromine left, we're giving this. We're doing SN1 and E1, so there's a possibility of doing metal shifts and hydride shifts, but since resonance stabilizes our most stable carbocation that we're gonna get, then we don't have to worry about doing metal or hydride shifts, and therefore we can just proceed to, in this case, do a nucleophilic attack, and we'll get this product. And then to get our E1 and to get our E1 product, we just have to analyze on the hydroids that our beta carbons have. So in here we have our alpha, and then here we have our beta. Remember that alpha is the one that is carrying that halide, and there are beta carbons they have hydrogens. So then we need a beta carbon with hydrogens to be able to do an elimination reaction. So then my beta on my left, it doesn't really have any hydrogens, right? Because if not, it will break an octet rule. But my beta on my right, it does have hydrogens. So then technically I am gonna be able to do an elimination reaction. So that's how I got that product right there. So that's why I said it depends, because sometimes our beta hydrogen, our beta carbons, they're sometimes not gonna have a hydrogen, just like this one on the left that it didn't have any hydrogen. So sometimes we're not even gonna have E1s and we're just gonna have SN1, or sometimes we're not even gonna have SN1 and we're just gonna have E1s. So SN1 E1 cannot happen on sp2 hybridized, meaning that if our positive charge is placed on a double bond, then we cannot see SN1s or E1s. So conceptual checkpoint: for each pair of compounds, identify which is expected to undergo solubilisis more rapidly in water, and explain your choice in each case. So then remember that solubilisis, there are gonna be reactions that are with water, so it's gonna be like this. So we're gonna have, I was gonna write HOH, but you can also write H2O. So then technically this is gonna go, you have to think about it in this way. what this conceptual checkpoint wants you to know, to think about, is that when you're what will be like your most stable carbocation. And we already said that we like primary, so then we like secondary over primary, we like tertiary over secondary, and then we like resonance stabilized carbocation stability. So then, for example, if for the first problem, if our bromine was to leave, we'll have a positive charge in here, right? And I would prefer this one, because that one is resonance stabilized, right? Well, this one's not really. So if we look at problem number 2, they look pretty similar, right? The difference is that halide. And remember what we said, on a periodic table, it's normally gonna go this way and this way. And if you think about it in that way, bromine is gonna be more reactive than a chlorine. Therefore, we're gonna like this one much better. And then for the third problem, we use the same logic as on the first one. If my group was to leave, I'll get a positive charge in here, and then this one will be much better, right? Because that one seems like it's resonance stabilized. Okay, so regiochemical and stereochemical outcomes for E1 reactions. So in solvolysis processes, there can be more than one elimination product. So then this goes to the logic that I told you. So then we have our alpha, right? We can always only have one alpha, because alpha is what's connected to that. It's directly connected to that halide. And we can have up to 3 beta. So then eliminations, they go with that our beta needs to have hydrogens. So this one has 1, 2, and 3. This one has 1, 2, and 3. And this one has 2. So then if you think about it, this one and this one, they are the same, right? So then if we do elimination reaction, if we do an elimination reaction for this one, or we do an elimination reaction for this one, we will get eventually to the same product. So then technically we'll get only one product from either of those two. So okay, so we have one product in here. And then if we analyze this one, we can do elimination reaction as well. So then therefore we will only have 2 elimination products. And of course, I can always just draw it out for you guys. Oops. So now just let me draw it more nicely for you guys. Okay, perfect. So then, let's see. So in here, we're gonna analyze this beta, and then in here, we're gonna analyze this beta. I just want you guys to remember on how to do elimination reactions. So then in here, we're just gonna remove that hydrogen. Oh, but wait a second. We are doing how's it called? We're doing E1 reactions. So then what we have to do first is doing our loss of a leaving group, right? So then we have a positive charge in here, and then we also have a positive charge in here. And then afterwards, we can actually proceed with our proton transfer, right? Okay, so then now that we have that, we have a positive charge in here, and then we have our negative placed in here. Then we have our let's see. We have a positive charge in here, and then we have this one in here. Then we have our negative in here. So then we can technically just, we can do a double bond between that negative and that positive. Okay, perfect. So then we have that one right there. And then we're just gonna ignore those hydrogens that we have in there. So this one, oops. So then, let's see. This one and this one are the same. I just kind of like hit those hydrogens that we had originally. And then in here we have right there. And see, we have the same product in here and in here. See, so it's just about knowing where that actual like those alpha and beta carbons they are, and then analyzing the hydrogens that they have. So more about E1 reactions. So keep in mind that sometimes some products can lead to a mixture of products, one being E isomer and another one being C isomer. Having that E isomer is being favored over the C isomer. Reminder that C is for cis and E is for trans. So then we like trans just because trans it gives a lower energy than cis. And this goes to the same logic that we've been doing before. In here we have our, at least for the elimination products, the substitution product is way easier than our elimination products. So then if our bromine leaves, we cannot technically do, so we have to, after our bromine leaves, we have to think about, can we do a metal or a hydrogen shift? But if we look at it, we have a tertiary already and there's no double bonds near it, so that will be the most stable that we can get to. So then here's our alpha still, and then here we have beta, beta, beta. So then my left and my right, they look the same, right? So then technically we are gonna get the same product no matter whether we look at it from left to right. And the one on top, it is a little bit different than the ones on the bottom because this one, it's a metal, but it also has 3 hydrogens, while the ones on the bottom, they have 2 hydrogens. We also need to consider one thing. The hydrogens are going to be in a wedge and dash. In here, I didn't really show it, just because if you think about it in this way, in this case, our product is going to be with hydrogens. They have the same group, therefore we wouldn't technically be able to tell which one has a higher priority, and we wouldn't be able to tell which one cis and which one's trans. Like if the whole figure is cis or trans, we wouldn't be able to tell. The same goes in here. We have the same things connected to it. We can tell which one has a higher priority in here. Which one will be the metal, of course. But then on this side, they're both the same. They're both metal groups. Therefore, we wouldn't be able to tell the priority. Therefore, we wouldn't be able to tell whether cis or trans. But in here, it's quite different, because the groups in here, they're technically different. So we will be able to tell which one has higher priority. So cis and trans matter. And this goes all the way back with E2 reactions. That remember that when we have a hydrogen wedge and a hydrogen dash, it means that we're possibly gonna be able to get cis and trans. So we're gonna get cis and trans products. So then when we do our elimination, for example, from the one on top, we'll get this product, which is quite nice. But then afterwards, we're gonna get our cis and trans. So then in here, we'll have a trans, and then this one, it will be a cis. So you can see that they shifted this one and this one. Okay, let's see. And also another logic. So then this one is our major product. And then this one are minor. Also, the thing is that we're going to the logic that we have things like mono substituted, di substituted, tri substituted, and then quarter substituted. So then the thing is that the more carbon bonds we have, the more stable it's gonna be. So this is the most stable or the most substitutions we can have. So then if you think about it, this one's dry, this one is dry as well, while this one is di. So it's less substituted, therefore it's less stable. So then, first we have our most stable trans, and then we have our least stable, because this one's dry. And then we go to di, because di is less stable than a dry. And then at last we have our substitution. So stereochemistry of SN1. So then remember, SN2 reactions, they proceed via inversion configuration. So then, for example, if our starter material is R, we're gonna end up with a product that's S. And then if starter material is S, we're gonna end up with a product that's R. So SN1 involves formation of an intermediate carbocation, which can be attacked from either side, leading to both inversion and retention configuration. Therefore, it means that we're gonna have 50-50%. So then that means that, for example, I'm not saying that this is right, but then if this was R, let's say, then we will get R and S as our products. So we will have two products. And then if this one's S, we will also get S and R. So we will get like 2 products from that. That's why I said 50-50. So then let's practice. So then draw the expected products for the following isobalysis reaction. So then for some of them, I'm not really gonna draw the product just because I want you to be able to know, like to be able to do like a little list. And to be able to tell me, okay, so E1 cannot happen because of this, E2 cannot happen because of this, SN2 can happen, or SN1 can happen. So I want you to be able to do that, because on a test, I think that's what matters most, because I think you can easily do a substitution. You can easily do an elimination. It's just knowing which one will be the products for that specific reaction. So then, okay, we first we can analyze this one. So for example, we have MeO-H. We said that normally E2s and SN2s, they proceed with a negative charge, right? So then we don't have a negative charge. Those ones seem pretty stable. So then we have E1, SN1. It would mainly depend on whether, we have, for E1, it would depend whether we have neighboring hydrogens for beta or beta carbons, if they have any hydrogens. So then after we analyzed this one and we saw that we have heat as well, therefore we wouldn't get SN2 with more major reason. We can, since we're doing E1 and SN1, we can instantly just do a loss of a leaving group. So we will get this, and we will notice that, well, it's resonance stabilized. So we cannot technically do any metal or hydroid shifts, so that's nice. So we would stay just like that. So we can just go from there, and then we'll get we can do a substitution right away. So then if we do a substitution reaction, we would just do a nucleophilic attack, and then we'll get, our oxygen with a positive charge. So then we can bring back our nucleophile, and then for it to remove that extra hydrogen that we have in, just to make it more stable. And then technically we're gonna look if we have any, like we have our alpha position, then we're gonna detect our beta positions, and we're gonna see if our beta positions have any hydrogens, so we can do an elimination. Luckily we do have, which will be the one on top. The ones on the left and the right, technically they don't have any hydrogens, so we only have one product, which is quite nice for elimination at least. So then we proceed as using MeO-H as a base. We remove that hydrogen, we put that broken bond, and we put electron pairs on that carbon right here. We make a double bond, like we said, we put those electron pairs on that carbon right there. Then we make a double bond between that negative carbon and that positive carbon, giving rise to our elimination product. And in this case, our elimination product is going to be our major, and then this one's going to be our minor. Okay, so draw it on your own. Draw all the expected products for each of the following isobalysis reactions. Okay, so now I want you to be able to analyze this. So then if we look at this one, we have ethyl OH. We don't have any, so I like to do a list. So we're not missing anything. So then we don't have any negative. So SN2 and E2, they're out of the way. We can do an E1 or an SN1. And it's also in heat, right? So definitely E1 or SN1. We're not able to do SN2, especially because we have heat and we don't have that negative charge. Also because I think I didn't mention this. So then we have a tertiary halide. So we know it's tertiary because of the number of carbon-carbon bonds we have. So we have 1, 2, and 3. And I think I'm stressing you guys a little bit with my battery of my iPad. So give me a second to get my charger. Yeah, I was kind of procrastinating on the idea of charging my iPad. I'm sorry if I sound a little bit tired. Is that having to record this all over again is not the best idea. But I'm glad that somebody else told me that the audio wasn't sounding on the video, because they did mention to me that you guys are gonna have a test pretty soon, maybe in 2 or 3 weeks. So I want you guys to be able to have this video. Okay, so try it on your own where we were. Okay, so we decided that we're gonna have an E1 and SN1. So easily we can use, the first step for an E1 or SN1 is just a loss of a leaving group. Therefore we can draw our lone pairs if we want to, of course. Then giving rise to a carbocation, right? We have a tertiary carbocation. We don't have any double bonds near it, so that's the most stable we're gonna get. So then I think you can visually see that we have, we have an alpha and then we have a beta or beta carbons. So then technically these beta carbons, they do have hydrogens in it. So then we are going to be able to have, we're going to be able to do an elimination, and we're also going to be able to do substitution. So then we're going to have a total of 3 products. So then in here, I do want to, in the bottom, I'm going to do my elimination possibly, and then my substitution, I'm going to do them in here. So that one can attack right there. We have a nucleophilic attack. And then, we're going to have our oxygen positive. So then we're just going to bring back our nucleophile. So then we can just remove that extra hydrogen. And that one will give rise to this product right here. So then for next, we're just gonna draw this one again. Now we're gonna draw this again because we have a total of 2 products. So we have like we said, we have our alpha, and then we have beta, beta, beta. So then these ones, they are alike. So that means that they're gonna give rise to the same product. That's why I said we only have two products in this case, because we have one and then we have another product in here. So then I'm gonna remove one from here, and then I'm gonna remove ones from here. So then I do ethyl OH. And you already know how elimination reactions work. We're gonna take that hydrogen from it. We have a carbon negative now, we have a positive now, and we can make a double bond between it, meaning we have this part right here, meaning we can get something like this. And here's just the same, it's just in a different position. So we get this, we get this. We have a hydrogen right here. We have a negative. We do a double bond between that negative and positive. Double bond, have our hydrogen. And then I don't really want to show my hydrogens, so it can look more like the product that we get. Like a product that we will possibly get on the book or something. So those ones will be my final products. Another thing that we have to now consider is the bulkiness of it. So then this one is not really bulky. So then I'm gonna teach you something. Since this one's not bulky, like it's not big or it's not too big, when it's not bulky, since we already know what substitution is, our major product is gonna be the most substituted, while our minor product is gonna be the least substituted. So when it's bulky, it's the total opposite. Our major is gonna be the least sub, and then our minor is gonna be the most. So then technically we said this one's not bulky, and we're gonna see whether our products are mono, di, tri, or quater substituted, I would say. So then this one's di, and then this one's tri. And I know that just by the number of carbon-carbon bonds I have 1, 2, 3 carbon-carbon bonds, and here I have 1, 2. So then in here I have a tri, so then that one will be my major, just because the most substituted. Then this one's my minor, and this one's my minor. So you'll be like, why the substitution reaction is not a major? Because substitution reactions, they're mainly major when we're doing it a primary, and this one is a tertiary alkyl halide. Since it's tertiary, normally other reactions other than SN2 are gonna be way faster, because SN2 rates go from like, it's gonna be faster on metal on primary, secondary, and tertiary, while on things like SN1, E1, and E2 is the total opposite. They're more faster on tertiary, secondary, primaries. So predicting products, substitution versus elimination. Substitution and elimination reactions are often in competition. Sometimes only one mechanism will predominate, or sometimes it will be the only one that's going to show up. So for example, we have an NaOMe. So again, things like Na, they're just as spectators. They're just there. So they're technically there, but they're not really gonna interact with each other. So that's why I only write NaOMe. So most of the time when I'm doing a test, when I see something like an Na, I just cross it out and then just write this. Okay, so perfect. So then we have E1, E2, SN1, and SN2. Okay, so then we said that E1 and SN1, they're normally like unstable, like on these things. They're normally like unstable things like OH, H, or like OCH3H. And by stable, I mean that they don't have any negative, they don't have any positive charges, nothing. So we do have a negative charge, so we cannot do E1 or SN1. We technically cannot do SN2 either. You'd be like, why? It's negative. Well, remember that we said on tertiary, this one is going to be a tertiary. And sadly, SN2s only happen on primary, secondaries, alkyl halides. While E2s, we can see it on primary, secondary, and tertiary. So SN2 doesn't happen on tertiary. Since this one is a tertiary, the only one that we're going to be able to see is going to be E2. Because we said that E2, it has that negative. But the thing is that this one is a tertiary. And, E2 tertiaries, they're the only ones that are going to be able to work out for this one. That's why it says that in here it's our only product. In other cases, two or more mechanisms will compete, giving multiple products, as seen in the following example. So again, we have as spectators, we have our OH negative. So we have E1, E2, SN1, and SN2. So then luckily this one is a secondary, which is quite nice. Sorry, my pen was getting kind of weird, so I tried to adjust it a little bit. Okay. So then this one has a negative charge, right? So then E1 and SN1, they're out of the way. But remember what we said previously, SN2s and E2s. SN2 happen primary, secondary. E2 happens on primary, secondary, and tertiary. And luckily, this one is a secondary because we have one carbon-carbon and two carbon-carbons. So it's going to be a secondary alkyl halide. Since we have a secondary, and we know that SN2 and E2 can happen on secondaries, therefore we're able to get those two products. So then in here we have our SN2 product, and then we have E2 products, and then E2 products we have let's see, we have we have two products just because of what we learned previously. They analyzed their beta carbons, and they saw that in here they have a hydrogen, and here they have another hydrogen. So then they were able to see that they had like they were able to see that they had like two products in total, just because this uh, beta carbon have a hydrogen, and then this beta had 3 hydrogens. We don't have any cis or trans because the products, we cannot technically tell, we cannot technically tell, priority groups right now. So we're not thinking about cis and trans. So they're just focusing on the amount of products we can get, which is 2. So we have 2 E2 products and we have 1 SN2. And you would say, why the elimination is the major? Again, SN2, the rate for SN2, it goes like this. So it goes from, by rate I mean like it's gonna be faster. So then this one's fast, and then this one is slow in this way. While on E2 rates, technically it goes from tertiary to secondary to primary. And then it's really fast and it's really slow. So you think about it, they're kind of like opposites. So E2 is really fast on tertiaries, secondaries, while SN2 rate is technically really fast on metals, on primaries, then secondaries, and then tertiaries, it technically doesn't happen on tertiaries. That's why elimination products, unless we have a primary halide, most of the time they're gonna be minor products over elimination reactions. So determining the function of reagents. So reagents are, they are what's a buffer arrow. So then nucleophiles are used for substitution, and then bases are used for elimination. Oops. So then things like DBN or DBU, they're really bulky, which makes them a strong base. So being a strong base, we know that elimination reactions work with bases, and we know the substitution reactions, they work with nucleophiles. So then if we have a strong base, it means that we have an elimination reaction. If we have a strong base, strong nucleophile, and then we have those negative charges, it means that we can either do Se2 or SN2. A weak base and strong nucleophile, it means that we can do SN2 reactions. Just so then only SN2, you can see they don't have any hydrogens. They're very electrophilic per se. They're very reactive. Just like we said, sulfurs are very reactive. Things like fluorine, bromine, chlorine, iodine. We have weak base, weak nucleophiles. So then you can get a hint that it's going to be E1 and SN1s. Just because, we said that they're at their most stable state. They don't have any negative charges. They just at its regular normal state. And again, therefore, reagents like DBN or DBU are used for elimination reactions in their strong bases. And I wanted to show you what DBN or DBU look like. Technically, on a test, they're not gonna tell you which one's DBN or DBU. But at least I want you to be able to see or to have like a visual concept of what DBN and DBU look like. So again, determining function of reagents, things like strong bases and strong nucleophiles can be used for SN2 or E2. So things like OH and OR, they're gonna be able to be used for SN2 or E2. But things that are really like reactive, like iodine, bromine, chlorine, things with sulfurs, they're just used for substitution and not elimination reactions. So then, since also because they have negative charge and they're very reactive, they're just gonna be for SN2 only. And things like weak bases and weak nucleophiles, things that they're really stable, possibly it's just gonna be for E1 and SN2 and not and SN1. So how to approach to this reaction? So in this example, NaOA is a strong nucleophile, strong base, while ethyl OH is a weak nucleophile, weak base. In a situation like this, NaOH is the reagent, while NaOH is the solvent in which the reagent is dissolved. If we look at our alkyl, it's a tertiary, therefore we could instantly eliminate SN2 reaction, giving it rise to an E2 reaction, and we only have one product because all our beta positions are the same. So that was a pretty good summary. So then I just wanted you guys to see this because in here we have two things on our arrow. Normally things on our top are what gonna be our base or our nucleophile depending on our situation. But things that are on the bottom, they're gonna be our what we call solvents. And then at the end of the video, I'm gonna teach you guys like which solvent is better for which type of reaction. So then if we do our little chart, E2, E1, SN1, SN2, and then we have something like NaOA. We already learned that Na is kind of like a spectator, and so then OA is gonna have a negative, right? So it's gonna be a negative charge. So then E1 and SN1, they're instantly eliminated. This one is a tertiary halide, right? Because we have 3 carbons, we have 1, 2, and 3. So it's a tertiary halide. And remember what we said? A tertiary, it can happen with an SN2. So that's why we only have an E2 reaction. And we only have one E2 product just because if we do our alpha and then we look at our beta positions, our beta carbons, they are the same. They all have 3 hydrogens. Meaning that no matter from where you get your hydrogen, it will give a rise to the same product. That's why we only have one product. And this is just a little chart that it can help you to see what outcomes you can get. So if you have strong base, weak nucleophiles, and it's primary, you can have E2. If you have strong base, strong nucleophile, and primary, you can get E2 and SN2 combinations. Have a weak base, strong nucleophile, primary, you can get an SN2. Weak base, weak nucleophile, primary. You can see that in this case we have weak base nucleophile, we have an E1 SN1 combination. We said that, remember that we said that this was kind of like rare to see on primary and secondary. That's why it has like a big X. While we do see E1 and SN1s a lot on tertiaries, right? So that's why we have a 50-50 combination. While in here, we have our strong base, strong nucleophile. So then we're gonna have like our things like OH, for example. And remember, SN2 reactions, it cannot happen on tertiaries. That's why we don't have any percentage of SN2s and we have 100% of E2, just because SN2 cannot happen on tertiaries. And you can see how SN2 increases over how we go from secondary and primary, and all goes all the way back to the rate that we said that SN2 rates goes that is fast on metal primary secondary, and then E2 rate is fast on tertiary secondary primary. Let's see. And how to identify which is major and which is minor. So when it's competing with SN2 or E2. Okay. Okay, so then we said that SN2s, they're normally only gonna be major when we have a primary alkyl halide. And from all the way down, secondary, tertiary, the major is gonna be E2 reactions. And you can see that concept in here. In here we have a primary, therefore our major is gonna be SN2. But keep in mind of the reagent for now. On secondary, you can see that our elimination now is gonna be our major product, and our substitution is gonna be our minor product. On our tertiary, of course, we don't have SN2s, we only have E2, so E2 is gonna be our major product. I told you to keep in mind of the reagent just because of the next slide. So then the thing is that it would SN2s will only be major if your reagent is not bulky, because if it's bulky, even if it's on a primary, then your major part is going to be E2. So then if you look in here, it's not bulky at all, right? Something like OH negative is not going to be bulky. And not bulky primary, then our major is going to be SN2. Well, if it's bulky primary, our major is going to be E2. So SN1 and E1. So then when we have both weak nucleophile and weak base, such as water or alcohols, in the absence of strong nucleophiles or strong bases, SN2 and E2 do not occur. So that means that when we don't have like a negative charge in our reagent, that means that SN2 and E2 cannot happen. Therefore, we can only have things like SN1 or E1. Therefore, we only have that unimolecular reactions. In other words, SN1 or E1. The product distribution SN1 versus E1 is affected by the densities of E1 products. When one or more of the possible E1 products is a tri or tetra substituted alkene, then E1 is favored over SN1. So then it's mainly like when we have like things like substitution playing in role, these E1 products are gonna be favored over SN1 products. So then here it goes all the way back. Since we already identified that this one's gonna be an E1 SN1, we can just do our leaving group. We technically cannot do like a metal shift or a hydroid shift, just because if you look at it, we already have a tertiary, we don't have a double bond next to it. Therefore, we already have it at its most stable state. So then, we're just gonna do, for this one, to get our SN1 product, we're just gonna do a nucleophilic attack. And then, we're gonna do our add-on step to remove that extra hydrogen that we're gonna get. And then to get this product in here, and this product in here, we're gonna analyze our alpha and beta carbons. and here I have an alpha, then here I have beta, beta, beta. If you look at this one, this beta and this beta, they're gonna end up giving me the same product, which is gonna be this one. Well, if I remove it, a hydrogen from here, I'm gonna get this product in here. And then this is gonna be tetra substituted. Okay, now we know the name, tetra. And then this one's gonna be 1, 2. This one's gonna be di. So then we prefer a tetra substituted over a di substituted. That's why this one's my major product, and then this one's my minor, and then this one's my minor product as well. So then regiochemical, stereochemical. So then personally, I had a problem like wrapping my head around the definitions from it. So I just wanted to give you some examples for the definitions. So regiochemical is mainly gonna be, for example, a more substituted product being favored over a less substituted product, unless it's really bulky, or a nucleophile attacking an alpha position. Or now for a stereochemical example, we can have things like inversion of configuration, how for SN2s we go from R to S, or like for some elimination reactions we have trans disubstituted alkene being preferred over a cis. So this topic can be a lot. So I personally had a tutor when I was taking this class. At least for this topic I had a tutor, and he helped me out to arrange this little list that I have for you guys. So then, as you can see in here, we have our SN2s or E2s, SN1 and E1. So you can see how we label SN1 and E1s together, because we technically SN1 and E1s go hand in hand. What determines, is our alpha and beta positions and whether we have available hydrogens to do our E1. And then let's see, if we look at SN2, they're not bulky at all, right? They're not huge. And we have a lot of spectators, right? Spectators, negative, negative, spectator. We have sulfurs just only happen on SN2s. So there's little things that can help us identify what reaction we're gonna do. Well, for example, E2, we also have a lot of spectators, but the thing is that these ones are really bulky in difference of SN2, that they're really small. The reagents that are similar in SN2 and E2, there are things like OH, NaOH, NaOCH3, and then NaOH. That's the most we're gonna get. After that, they don't have similar reagents. Well, SN1 and E1, they don't have any negative charges. They don't have any of those negative charges at all. Some other things to consider is that SN1 and E1, they can happen in heat. Heat is normally shown in triangles, or it says heat under the arrow. SN2 happen at room temperature, and E2 can happen in heat as well. So then you can see technically that we have this rate that SN2 reactions, they're kind of like different from the other reactions, like SN2 happen at room temperature where everything else happens on heat. Everything else can happen on a tertiary, except that SN2 is done. And we're gonna learn in a little bit that SN1 and E1, they like product solvents, while E2 also like product solvents, and exception is gonna be SN2, in which they only like a product solvents. And again, I wanted to give you guys a little summary that SN1 and E1, they're primary, secondary, tertiary. SN2, primary, secondary, no tertiary. And then E2, primary, secondary, and tertiary. So I was gonna initially solve this for you guys, but like I said, I think you guys are able to um like solve or eventually get to the product. But I think the most problem that you're ever gonna get is that sometimes you're just not able to to identify what reaction you're able to do, like if it's gonna go under E1 or E2 or SN1 or SN2. I think that's the main issue, is like identifying what reaction you're able to do for the substrate that you're giving and for the reaction that you're given. So for example, in here we have an NaOH. Na is an spectator, so then we just have this. We also have to consider that our substrate is going to be a tertiary. So then we have a negative. So then we can technically eliminate E1 and SN1 from our possible reactions. So we can do E2 or SN2. So then we have a tertiary. That means we cannot do SN2s. So we can technically only do E2. Thinking about that, we can only get E2. We can start looking at our alpha and then our beta positions. So then this beta and this beta, they are the same, so then we will get the same product. So then we have one product. And if we analyze this one, it will be different. So then we have two products. So then if we eliminate, let's see, if we do elimination from this hydrogen, for example, then we will get rise to this, we get a rise to this product right here. Wow. Sorry. Well, if we eliminate like this hydrogen from here, then we'll get this product down here. And we also have to think about this too, that this one's not bulky at all. And remember that we said when it's not bulky, our major product is gonna be the more substituted, while our minor product is gonna be the less substituted. In this case, we have a di substituted, and then in here we have a tri substituted. That's why our tri substituted is gonna be our major, while our di substituted is gonna be the minor product. Okay, so then in here we have a net spectator. It gives rise to the O metal negative. So then we have a negative. That means that we're gonna do SN1 or E1. We have a secondary, so then that means that we're possibly gonna be able to do E2 and SN2. It will all depend on the available hydrogens. So then E2 and SN2, we don't really have to worry about any carbocation rearrangements, just because everything happens simultaneously at once, which is pretty nice. So that's why I was able to right away, just get my SN2 product, because this one, for SN2, we just do a nucleophilic attack right away, and then this one leaves. right away. And we just have a reverse of configuration. So then you can see how in here we first had this one, like it's still on a normal bond, you can see, but then it kind of it's kind of like this carbon flip. So technically this one it went from wedge to dash. It's still, that O metal is still on the same position as that bromine, but we just wanted to show how it went maybe from R to S or S to R. So we're able to get our substitution product. And then we can get our elimination product. Let's see. So then for elimination, we have to analyze all our beta carbons. So then we have one alpha, and then we have two betas in this case. So then here we have a beta hydrogen. And then in here we have 3 hydrogens. So then technically they're different. So then we have 2 different elimination products, as you can see. This will give rise to, this will give rise to this product down here and this product down here. Since this one's not bulky at all, we have the same logic that our major product is going to be the more substituted. This one's more substituted just because we have CH, we have a carbon bond, we have a carbon bond, and here carbon bond, it means it's twice substituted. Well, here I only have one carbon bond, which means that it's going to be mono, and it makes it a minor product. This one is also minor because this one is on a secondary, and we said before that normally we need a primary, not bulky, for SN2 to be the major product. Some rules that we have to remember when, for example, we learned the steering wheel method for E2, or bromine and or leaving hydrogen, they have to be on normal bonds. So then normal bonds, it means that it's not on a wedge or on a dash. So bromine, it is on a normal bond, but our hydrogen, it's not. So we're just gonna rotate. So you can see that I have my dash, my wedge, and my normal bond. So I kept them on the same positions, on the same order of dash, wedge, and normal bond. I just changed the order of, in here I have my cyclo, then I have my CH3 and hydrogen, and then I just changed the order to a hydrogen cyclo to CH3. So I just rotated. So then I can have my hydrogen on a normal bond, and then after that I can proceed to eliminate those two or remove them, so I can place them on a double bond, or I can make a double bond between them. So then afterwards I have my, if you can see, I have my cyclo on a wedge, so I put it up, and then I have my CH3 on a dash, so I put it down. And if I look at my other carbon, I have a CH3 on a wedge, so I put it up, and then I have a hydrogen on a dash, and I put it down. So in this case, we didn't really have to look at cis or trans, which is very nice. But if you do, it is really important to be able to master that, whether it's gonna go up or down. So then remember, when it's on a wedge, it's gonna go up. When it's on a dash, it's gonna go down. Okay, so we can try it on your own. Identify the major and minor products that are expected for each of the following reactions. So in this case, we're gonna do a little chart. We're gonna do E1, E2, SN1, and SN2. So then, again, at spectator, chlorine, we're gonna have a negative. So then we said when it's like really, really reactive, just like a chlorine by itself, no hydrogens or anything. And when it's especially a negative, so we can eliminate E1 or SN1 right away. But the thing is that E2s, we normally have a hydrogen next to it. They're not just, chlorine by itself or bromine by itself. So E2 won't be able to happen. So SN2, it's going to be able to happen. So then remember, SN2 happens everything at once. Everything happens simultaneously. So then that means that my chlorine is going to attack it, causing a loss of a leaving group. Another thing that we have to keep in mind is that with SN2s, we have reverse of configuration. So then you can see I didn't put my chlorine on a wedge. Instead, I put it on a dash, taking place of that bromine. And then again, so then this one's going to be my, I don't know what happened in there. So again, this is going to be my only product. And then in here, I'm going to do my same logic again. E1, E2, SN1, SN2. So then you saw that sulfur, right? So you can technically already think, well, doesn't seem like E1 or SN1 is going to happen. Especially if we have an spectator. Also remember we said sulfurs only happen on SN2. So then we can eliminate those ones right away. So then we're going to have a nucleophilic attack again. Having a loss of a leaving group. And then it's just going to take place of that iodine. And that's going to be my only product. Okay, so is just extra stuff. I'm not sure if we're going to cover that on class, but we did cover that on my organic chem class, and it's on the book as well, so possibly just in case, So there's other things, substitution and elimination reactions with other substrates. So we're gonna have something called cyanide ion, which is NaCN, or it also looks like this. So that one, as you can see, we can do a primary or a secondary substrate. So when it's primary, we can get an SN2. While when it's a secondary, we can have an SN2 and E2. And, everything depends on the amount of products. It depends on the betas, on the alpha, on the betas. And since we're doing SN2 and E2, it means that we don't really have to worry about, carbocation rearrangements or anything. Another thing that we're going to look at is tosylates and sulfonide ions. They're excellent leaving groups, just like halide ions. So then, sadly, you have to wrap around your head that this thing is the same thing as this, or it's the same value. So by same value, I mean that they're gonna be treated the same. So then we have tosylate variations. So then we have different variations. So this is kind of like the resonance structures for a tosylate. And this is just different representations of a tosylate. So like we said, tosylate, we just treat it just like if it was like a halide. So when forming tosylates, we retain our configuration. So it's technically like we're replacing our leaving group with a tosylate. So you can see we're just gonna retain the same configuration. And when you have to convert to tosylate, you're gonna this is gonna be your reagent. So you can see we kept that wedge, and then we just replaced that leaving group with a tosylate. So when treated with a strong nucleophile, the tosylate acts just like an alkyl halide. Therefore, it will just go through an inversion configuration. So you have to visualize this as just a regular halide. So then, if I was doing just if I was just doing a normal reaction, just like always, and thinking, oh, this is just like a chlorine right there. So then I would think about it, oh, let me do my little chart, E2, SN2, and SN1. So we have a negative charge. So then E1 and SN1, they're out of the way, right? And I can technically just look at it and maybe E2 or SN2. Also, this one is a secondary, right? So it is a big possibility we can do E2 or SN2. The thing that says that we cannot do E2 is because this one, bromine is very reactive. Bromine negative is very reactive. So E2 is out of the way. So SN2s are only possibility. So SN2s normally start with a nucleophilic attack first, causing a loss of a leaving group. And remember, SN2s, we have inverse of configuration. That's why I didn't place it, or we didn't place it on a wedge. Instead, it's on a dash. And it went from S to R. So tosylates. So remember, they're just like a halide. So primary tosylates, when primary, not bulky, the major is gonna be an SN2. Secondary, not bulky, the major is gonna be E2. So conceptual concept, predict the major and minor products for each of the following reactions. Okay, let's see. So then again, we have an spectator, we have an SH. So then we have SN1, E1, E2, SN2. So we have a negative, so E1 and SN1, they're out of the way. E2, technically what gives it away is that sulfur, right? So then E2 cannot happen, so we only have SN2. So luckily we don't have any wedge or dashes to deal with, so we don't really have to worry about inverse of configuration, which is quite nice. So we're just gonna do a nucleophilic attack, and then remember, tosylates, just read them as just regular chlorines or bromines or iodines. So the nucleophilic attack causes a loss of a leaving group. So then that will be like my final product. So then remember what we said, when we have this as a reagent. So then when we have things with step 1 and step 2, it's kind of like it's telling you like one arrow, and then you get your product, and then you do your other arrow, and then you get your product. That's what's kind of telling you. So Terbutyl, okay, is not your solvent in this case. I just wanted to clarify that just in case it was a bit confusing. So then we're first gonna do a tosylate. Remember, a tosylate, when we're creating a tosylate, we're not doing any reverse configuration, nothing. We're just gonna replace our leaving group with a tosylate. So our product for our first step is just gonna be this. We still remain on a dash. And it's gonna look like just like that. And then we have Turbu, okay, or I normally write it just like that because it's a little bit much easier. Okay, so after that we can do a little chart. You have SN1, E1, E2, SN2. Oops, sorry. Okay, so it's a negative, so E1 and SN1, they're eliminated. We have to remember their view, okay? It's really bulky, so SN2 cannot really happen. So we have E2, so we can look at our alpha and we can look at our betas. So we have a beta hydrogen in here, and then we have a beta hydrogen in here. So then technically, luckily, we don't really have to focus too much on doing the rotating wheel, just because, you know, we're looking at similar groups in here, and these ones are just hydrogens. So it's gonna be really hard to tell priority groups, so we don't really have to look at that. But we can infer we're gonna have two different products, just because in here we have only one hydrogen, while in here we have three hydrogens. So we're gonna have a total of two products. So if I was to eliminate from here, I'll get something like this. Let's see. This one lives. Let's see. And then we're doing E2, so we're not doing any carbocation rearrangements. We take that one, that's it, this one lives. Okay, so we have this, 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 and this. Then we'll give rise to a trisub. And then if I were to move one from here, so then in here we have a hydrogen, this one left, have this in here, and then this one, and this one. And I know that one looks really gross, so let's eliminate those hydrogens that we have extra right there. So then we only have this and this. And our product should look something like this and something like this. that one will be mono. So since this one is really bulky, remember when it's really bulky, when it's bulky or major, it's gonna be the less sub, while our minor is gonna be the most sub. So that means dry sub is the most sub, so this one will be my minor product. Well, this one will be my major product. Okay, so solvent effects and substitution reactions. So then SN2 reactions require polar solvents. Polar solvents can be classified into two categories. We have product solvents, which contain a hydrogen atom connected to an electronegative atom, and we have polar aproduct, in which lacks a hydrogen atom connected to the most electronegative. So what are product and polar aproduct solvents? Like it said, product solvents is when you have a hydrogen directly. So we have a hydrogen directly attached to the electronegative. While in polar aproduct, it doesn't mean like that we don't have any hydrogens, because you can see here we have hydrogens. The thing is that there's no hydrogens connected to that most electronegative. So not directly connected. And also we all took English class, so A is for not. So then aproduct not directly connected, while product is directly connected. And I just wanted to show you guys like the rate charts. So effects of solvent of SN2, polar or product, they will speed up SN2 reactions. So polar or product, they are the ones that they don't have it directly connected to it, they're not. And you can see here that it just increases the rate. So increase in rate due to polar product solvent. While you can see that SN1 reactions, they prefer polar product. And polar product is the ones that, they have a hydrogen connected to the most electronegative. And you can see the rate, this one versus this one, and you can totally see that they do prefer things like polar product over, they prefer things with polar product over polar aproduct. Okay, perfect. So thank you so much for taking the time to watch this video, and I hope you have a wonderful day.